Hello, I hope you are doing well. In this video, I will introduce a tool called MDDPlatform. Once you run this tool locally or deploy it on the internet, you'll be greeted by a page featuring a navigation menu on the left, which I'll be discussing in this video. To kick off your journey with this tool and forge a software solution anchored in the model-driven development paradigm, it's essential to outline your problem's boundaries. The problem domain section is where you can chart out the problem domain, decompose it into subdomains, and construct models for each at varying degrees of detail. Modeling necessitates a specific language for articulation. Within the DSL management area, you're empowered to craft domain-specific languages that will enable you to describe your models. A crucial component of model-driven development is model transformation. In this process, input models are subjected to a transformation that converts them into an output model. This transformation process progresses from higher to lower levels of abstraction until the desired solution or code is generated. This section allows you to explore transformation patterns and use them to transform your domain models. The MDD platform has also introduced a feature known as pipeline. This functionality allows you to arrange a series of transformations. When you execute this pipeline, the transformations proceed either automatically or with some manual input, transforming the initial models into their final versions. The process culminates with the successful execution of the last transformation in the sequence. The whole model-driven development approach can be envisioned as a comprehensive process. The process management section is where you can define, configure, and then execute this process. This procedure, whether automated or semi-automated, will lead to the generation of your final model or the code for your solution. In the settings section, you have the option to reuse shared artifacts such as domain-specific languages, transformation patterns, and MDD processes. You can incorporate these into your project and utilize them for its development. I will delve into each of these features in greater detail in upcoming videos. One of the challenges that model-driven development MDD faces is the high initial cost associated with adopting model-driven approaches. To produce a software solution using MDD, one must utilize a domain-specific language, DSL. This involves either creating a new DSL or using existing ones, followed by writing a series of model transformations with model transformation languages to ultimately generate the solution code through these transformations. To reduce the initial costs of this approach, it would be beneficial to reuse DSLs defined by others, as well as model transformations. When you first launch this tool, the domain-specific languages and transformation pattern sections may not contain relevant information. You can navigate to the settings section to add the packages we have predefined for your project. We have delineated several DSLs and the concepts pertinent to these languages, which are available for reuse with a simple click of a button. Furthermore, we have established a collection of transformation patterns that are likely applicable across various projects, along with a suite of MDD processes that can be adopted for your project. Currently, I have integrated some DSLs into my project, along with various transformation patterns and MDD processes. You can access this section to view the DSLs and transformation patterns that have been added for use in your projects. In subsequent videos, I will elucidate how you can define your own DSL or employ transformation patterns. Suppose you intend to create an online ordering system. The first step is to define the domain of your problem. For this purpose, navigate to the Problem Domain menu. Here you will define the domain of your problem by specifying the title and providing an explanation for it. As an example, I will define the scope of my problem. Once you have defined the problem domain, you can break it down into different subdomains. For instance, the online ordering system can be described from various perspectives such as customer management, product management, order management, and shopping cart management. Each of these aspects can be defined as a subdomain. To do this, click on the Decompose button and define the subdomains, one for order management, one for product management, one for customer management, and one for shopping cart management. Now you can describe each of these subdomains using different models defined at various levels of abstraction. In the upcoming videos, I will demonstrate how we can define models at different levels of abstraction. After defining the problem domain and decomposing it into various subdomains, we can now define and describe each subdomain from different perspectives at different levels of abstraction. For each subdomain, we should be able to define models at various levels of abstraction. Let's consider defining these for the order subdomain. I will click to be redirected to the page designed for defining these models. To define each model, we assign a name to it and may also assign a tag. The tag is optional, but it can convey various information about the models. Currently, a specific function related to the tag is not defined in this tool, but its functions will be defined in the future. For instance, you might assign the draft tag to distinguish your draft models from others, or use tags to indicate whether the model is publicly available, or whether it is a private model, or it is a read-only model, or you can change its specifications. Currently, the use of the tag is optional, and you can input the data you wish. In the tag section of the model definition, I will mention the language in which the model is described. Let's define a model as an example. I will also specify the tag in the type section. We determine the level of abstraction for the model, whether it is at the CIM, PIM, PSM, or code level. In this example, I define the model at the CIM level and set its sublevel to 1. This sublevel allows us to have different layers of the model at each level of abstraction, such as at the CIM level. For now, I will set this to 1. In this section, we select the meta model or the language we wish to use to describe the model, and I will choose this meta model. I will explain what these meta models are and their structure in a separate video. Now I click on this button, and the model is defined. Defining models at different abstraction levels can be a tiring and time-consuming process. There is also the possibility that, within a given architecture that follows a specific design pattern, we may need multiple levels of models based on a single set of metamodels. Later in other projects, we might want to reuse those same models, defined with the same languages and at the same levels of abstraction, without having to redefine them one by one from scratch. Therefore, once you have defined a hierarchical structure of models in this way, you can package these abstraction layers into an independent package. This package can then be automatically reused across other subdomains to generate the corresponding models. For example, let's say I want to define the same abstraction levels for the product subdomain, where I don't yet have any defined models. These abstraction levels are supposed to be the same as the ones I previously defined for the order subdomain. On this page, I click on the Create Package link, which takes me to a page where I can see the models I had already defined in the order subdomain. Here you can assign a title to your package. For instance, I add a title, and then I can edit the names of the models or define a more generic naming convention so that the package can be reused across any subdomain. Another approach is to parameterize these names using expressions that can be interpreted dynamically. For example, instead of hard-coding the word orders, I can use a placeholder expression that adapts the model names based on the subdomain. Let's apply this substitution to the other models as well. Once I finalize the naming, I can create and save the package. The package then appears in my list, ready to be used. Now I can reuse this package to define models for other subdomains. For instance, if I want to apply it to the products domain, I open the package, select the domain I'm working on, and specify which subdomain is targeted. Suppose I select the products subdomain. The model names are automatically adjusted to fit that subdomain. The same works for the customers and cart subdomains. After clicking Create Domain Models, the system generates the models for me. When I check the generated results, I can see that the models are indeed created, but this time customized to the product subdomain. I can repeat the process for any other subdomains, like customers, by simply clicking Create Again. In this way, you only need to define the abstraction levels once, encapsulate them in a package, and then reuse that package across different projects and problem domains to automatically generate the required models. There is one more point I mentioned briefly in another video, which I promise to explain later, related to the settings section. When you install this tool for the first time, you won't yet have any packages available. To get started, you can import a template package from the settings section. By clicking the Ruse button, the tool will generate a package containing the abstraction levels I demonstrated earlier. When I navigate to the package section, I can see that this is indeed the same package I imported from the settings, and I can now use it directly in my projects. After defining models at different abstract levels, we can analyze our problem domain. There are various methods to analyze the problem domain. We have proposed a method called CRAC, which I intend to briefly explain in this video. In the CRAC method, We first attempt to identify domain concepts and entities. Every system likely possesses a series of high-level functionalities, tasks, or requirements that must be fulfilled. We model these high-level functions in the form of commands. When a command is executed in the system, it can transition the system from one valid state to another, which we represent this fact as an event. We delegate the management of a command and its responsibilities to a concept determining which concept has the duty of managing that command. This is modeled using the is responsible for relationship between a concept and a command. We also model the potential event that may be published during the execution of a command through the publish fact relationship. An event may occur within a system, serving as a trigger that necessitates the next action or the execution of another command. We address this through the call for action relationship. Sometimes an event may transpire in the system, resulting in the publication of an event that a part of the system is keen to be informed about. This is modeled using the is interested in relationship between a concept and an event. It is important to remember that these models are analytical models and not intended to describe the intricate details and complexities of design and implementation at this stage. In a subsequent video, I will demonstrate how to define a CRAC model for the online ordering system in the order subdomain. In the previous videos, we explained CRAC models in this method. In this video, I will demonstrate how to create and build the CRAC model for the order subdomain. We navigate to the order subdomain and select the first model, which is based on the CRAC model. Now let's begin describing and defining this model. One of the domain concepts we encounter is the concept of order. Another concept is customer, where each order corresponds to a customer. Additionally, an order can consist of one or more purchased items. After defining the domain concepts, we can model high-level functional commands. For instance, we should be able to create or cancel an order, as well as complete an order if everything is in order. We assign the responsibility of managing these commands to the order concept. To achieve this, I'll define these concepts in this section. In the CRAC meta model, a relationship called is responsible for connects the concept to the associated command. Let's define the commands and their responsibilities. For example, we'll create an order, cancel an order, complete an order, and handle order revocations. After defining these, we save our changes. Additionally, events may occur in the system that we want to track. Suppose a new customer is defined and created elsewhere in the system, for example, the customer management subsystem. In that case, our orders management subsystem should be informed. To achieve this, I establish an interested in relationship between the customer concept and the customer created event. With the concepts defined and commands created, we describe the potential events resulting from executing these commands. For instance, the create order command may succeed, resulting in the order created event, or fail, triggering the create order rejected event. We save these event definitions. Similarly, we define events for cancel order and other relevant commands. Now, our domain concepts, commands, and events are defined. To check the status of our model, we can view its diagram. You'll notice the relationships among the concepts and their responsibilities. Additionally, we're interested in being notified when the customer-created event occurs. After describing the CRAC model, we need to fill the models at lower levels of abstraction using a series of transformations. These model transformations are executed sequentially, transforming our input model into the output model. Finally, PSM-level models as well as code-level models should be produced. To manage this process and guide it effectively, we need a clear methodology and process. Just as creating software requires a well-defined approach, executing these transformations, whether they involve input models or output filling, also necessitates a process. One of the features provided by this tool is the ability to define model-driven development MDD processes and apply them to different projects. In a separate video, I will explain how to define an MDD process. For now, let's explore an example of the process we proposed and presented. In previous videos, I mentioned that in the settings section, you can add domain-specific languages, transformation patterns, and MDD processes to your project for reuse. If you've already clicked the Reuse button, you'll find two processes on the Process Management page. 1. A model-driven development process that transforms and refines models from the CIM level to the PSM level. 2. another process that converts PSM models into C# language on the .NET platform. Let's take an overview of the model-driven development process to understand how it works. Generally, processes, whether MDD processes or other software development methodologies, consist of several phases. Each phase can include one or more activities, and each activity can involve one or more tasks. The finest grained unit of work is the task. For example, the process we propose consists of several phases: an initial phase, a phase for building CIM models, a phase for building PIM models, a phase for building PSM models, and the final phase, which is the code generation phase. The initial phase includes an activity aimed at exploring the problem domain. Within this activity, there are two tasks. Task 1, preparation for holding a workshop using the CRAC method. Task 2, creating the CRAC model. In the CIM model construction phase, we transform CIM level models to other models defined at the CIM level. The refinement process involves several tasks. In the PIM model construction phase, here we convert CIM level models into PIM level models. Additionally, we refine models derived from the CQRS pattern and detail models built based on the API controller pattern. The activities in this phase specifically describe core domain concepts. At PSM model construction phase, we have a series of activities. First, we convert PIM models into PSM models. Next, we further refine the controller model, adding more details. PSM models derived from the CQRS model, and core domain models undergo similar refinement. Finally, we describe the details of data repositories and create interfaces. And the last phase is the code generation phase. I have not added details to this phase because we defined a separate process for code generation. The goal was to have two processes. By executing the first process, we can convert the models to the PSM level. Then by executing another process, specifically the process of transforming the model to text, we can convert the model into solution code. With this approach, each of these processes can be executed and configured independently. In the next video, I will explain what we need to do when executing a process. The processes defined in this tool are high-level processes that do not depend on a specific problem. Instead, they are generally defined, and we can reuse them for different projects or different problems, provided that the architecture and design patterns we are considering align with those included in the process definition. If we want to implement a project with the same structure and architecture, we can reuse that process. Before using the process, we must configure it because in the initial step, the process is defined in a general manner and has no dependence on a specific problem. Now, what is meant by process configuration? Generally, processes consist of several parts. At the highest level, there are phases, and each phase is broken down into activities. These activities, in turn, are further divided into tasks. In fact, the fine-grained unit of work in a process is a task. In MDDPlatform, we can have two types of tasks: manual tasks and automatic tasks. A manual task expresses what a user should do, for example, refining a model or entering information. On the other hand, an automatic task can be executed automatically. Automatic tasks in MDDPlatform correspond to transformation patterns, and task execution is equivalent to calling or executing a transformation pattern. When we say that we need to configure a process, we mean configuring these automatic tasks. It involves determining the inputs for this task and understanding what the output of the task will be. Since each task is mapped to a model transformation, the inputs and outputs of the task correspond to the input models and output models of those transformations. Therefore, when using a process, the first step is to configure it. Configuration entails specifying the input models and output models corresponding to the automatic tasks. In another video, I demonstrate how to configure this model-driven development process for an online ordering system. Next, I'll show how to run this process after configuration and obtain the solution code. To configure the processes, what we need to do is select the process we want to configure and then create a configuration for it. We click on this button and I assign a title to it. Next, I click on the Create button. Now, when I return to the Configuration section, I can see the configuration that I created. If I click on the View button, I notice that currently no parameters have been set for those tasks. During the configuration process, I'll need to specify these parameters. To perform the configuration, I click on the Config Task button. I then specify the purpose of this process. In my case, I'm configuring it to create and prepare the online ordering system. I select the problem domain, and you can see that the list of automatic tasks defined in this process is displayed. For each task, I must specify the input and output models. In the supplementary file that I sent along with these videos, you can find information about the input and output models for each task. Use this information to configure the tasks accordingly. For example, to configure the first task, I consider the CRAC model as input and the CIM model as output. I click on the Config button, set the parameters, and save it. Similarly, for the second task, I designate Model 1 as input and Model 2 as output, saving the changes. For Task 3, I consider Model 2 as input and Model 3 as output, and again, I save the changes. I repeat this process for the remaining tasks, following the information in the supplementary file. To avoid making the video too lengthy, I'll pause the recording and configure the remaining tasks in the same way as demonstrated earlier. Now that all the tasks are configured and the input and output models are set, we can click on the Create Executable Process button. This action combines the process information and configuration details, resulting in a concrete process that can be executed. If I navigate back to the Process Management and Configuration section and click on Execute Process, the process that can be executed will be displayed. In a separate video, I'll explain how this works. After configuring the process and creating an executable process, we can run it. To do this, navigate to the Configuration section and click on Execute Process. Here you'll see a list of tasks that will be executed as a result of running the process. Some tasks have a Done button associated with them. These tasks require manual description or refinement of a part of the model. The remaining tasks are automatic and run automatically. They correspond to model transformations that convert the input model to the output model. Now let's proceed with executing this process. The first task involves holding a workshop to analyze the problem domain using the CRAC method. Assuming we've completed this workshop, we can click the Done button. The next task instructs us to create the CRAC model, which we previously discussed in our videos. I'll mark this task as done, allowing us to continue the process. Clicking Continue, we see that these two tasks are executed, and we move on to another task. In this task, we need to describe the characteristics of the domain concepts in the CIM model. Here's what we want to describe: order, TMO customer, and order. For order item, we describe properties such as ID, name, quantity, unit price, and total price. For customer, we describe properties like ID, email, first name, last name, address, and country. For order, we describe properties such as ID, order state, total amount, and currency. Additionally, the concept of an order is related to the concept of a customer. Each order belongs to a customer, and an order may consist of one or more items. Let's proceed to describe the CIM model based on this information. From the list of models, select the CIM model and define the domain concepts. For instance, describe the customer properties, define the ID feature, along with other properties like email, first name, and last name. Save these changes. Similarly, for the order item, define an ID property, unit price, and total price properties of type long, and quantity property of type integer, and a name attribute of type string. Save these changes as well. For the order, define a status property, an ID property, a total amount property, and a currency property. Additionally, create two relationships, has customer and has order items. For has customer relation, set the relation title as customer, and the destination of the relation should be the customer concept. Set its multiplicity to 1. For has order items relation, set the relation title as order items, and the destination of the relation should be a collection of order item. Save these changes. With the desired model described, click Done to continue the process. Next, we encounter another manual task where we need to enter the commands and events attributes of the CQRS model. I'll cover this part in a separate video. The next step is to define the properties of commands and events in the CQRS model. Within the CQRS model, we have commands such as create order, cancel order, complete order, and revoke order. When creating an order, I require both the order ID and customer ID. However, for canceling, completing, or revoking an order, only the order ID is necessary. Regarding events, when a command is executed, resulting events can include relevant information. For instance, order created and order canceled events may contain the order ID and customer ID. Additionally, if a request is rejected, e.g. an order creation request, I can include details like the order ID, customer ID, the reason for rejection, and related error codes in the published event. The customer-created event can similarly encapsulate essential information, such as customer ID, first and last name, address, and country. To ensure consistency, I define this information within the CQRS model. For example, when creating an order, I gather these two items and click the Save button. Conversely, canceling an order requires only the order ID. Similarly, I specify the remaining information for other events, such as order created. If a request is rejected, the associated event will include the properties I've described. I also describe the customer-created event. Now I can return to the MDD process and click on this section. In the next part, I need to describe the collaborators of command handlers and event handlers that assist in achieving their goals. I'll cover this in an upcoming video. At this point, I need to define the collaborators for the command handlers and event handlers. If you recall, the first model we implemented was the CRAC model. In this model, we identified and modeled commands and events. Subsequently, a command handler is automatically created for each command in the CQRS model at the PIM level through transformations. Similarly, for each event that a domain concept is interested in, an event handler is generated at the PIM level within the CQRS model. To handle a command or an event, I likely require an interface or service that can implement the necessary functionality. For instance, let's consider a handler named createOrderHandler, responsible for processing order creation requests. To fulfill this requirement, I need an iOrder repository interface to interact with the data repository, storing order information. Additionally, I must retrieve information about the shopping cart, which can be achieved through the iCart service interface. Similarly, the iCustomer service interface provides access to customer information. During command execution, one or more events may be published. To handle event publishing, I rely on an iMessage broker. Mapping domain events to messages and sending them also requires an iEventMapper interface. These interfaces collectively enable the high-level functionality described. Likewise, for other handlers, we can define corresponding collaborators. The same approach applies to event handlers. For example, the customer-created handler handles the customer-created event. Upon receiving this event, I store customer data using the iCustomer repository interface to communicate with the repository. In the CQRS model at the PIM level, I navigate to the command handler section. These command handlers are automatically generated through model transformations, and I only need to provide additional information. For instance, I specify that collaborators should be of interface type and define collaborators for the command handlers. Once I've defined collaborators for the command handlers, I repeat the process for event handlers. With this stage completed, I can click the Done button for this task and proceed with the MDD process. As the process execution continues, we encounter another manual task that requires completion. I will explain how to perform this task in the next video. To perform this task, I need to specify the features of the endpoints. The request must be entered into this system in some way. I use the controller pattern to manage these requests and employ the API controller. Now I have to determine the path for accessing each of these endpoints. Which endpoint should receive the HTTP post and HTTP GET requests to ensure the appropriate response? For instance, these endpoints are automatically generated using transformations in the controller model at the PIM level. We have one endpoint for managing order creation requests, another for canceling orders, one for completing orders, and yet another for revoking orders. Additionally, we define the access route for these endpoints. I will describe this information in the controller model. To do so, I navigate to the controller model at the PIM level and open the HTTP POST endpoint. The necessary information is automatically generated through transformations, so I only need to set the access route for these endpoints. For example, I choose the create relative path for one endpoint and specify that the user must be authenticated to accept this request. Similarly, I set the cancel route for the cancel order endpoint and define access routes for the remaining endpoints in a similar manner. Once I've entered this information, I consider this step complete and proceed by clicking the Done button to continue with the rest of the process. Moving on, I encounter another manual task that requires me to express and describe my core domain design concerns. I've designed this based on the domain-driven design (DDD) approach at the PIM level, specifically using the entity pattern. As we know, entities have a unique identifier. At the CIM level, I've already described these entities, and now I simply need to specify which attribute I define for domain concepts serves as the unique identifier for each entity. For example, I had concepts like order, order item, and customer at the CIM level, with various attributes associated with them. Rather than redefining these properties in the core domain model, I explicitly state that the id feature serves as the unique identifier for the order entity. I do the same for order item and customer. When I open the core domain model at the PIM level, I see that these entities have been transferred here through model transformations. I only describe that this entity has an entity ID of type guide with the name ID. I repeat this process for the other entities as well. There's no need to define additional properties because I can transfer and obtain this information through transformations. With this step completed, I click the Done button and proceed. As I observe the execution of model transformations, I realize that there's another manual task ahead. To keep the video concise, I'll address this task in the next video. In this task, we are at the PSM level, where we will describe the implementation concerns for the controller model. At the PSM level, model descriptions are platform-specific. Since I plan to use the .NET framework and later generate code with the C# programming language, it is necessary to outline the implementation concerns related to this platform. For instance, within the .NET framework, realizing the functionality of the controller requires using certain Microsoft-provided packages and libraries. Therefore, I need to define the relevant package in the controller model at the PSM level and specify that the order controller will utilize this package. Let's proceed. Upon opening the controller model at the PSM level, I notice that the order controller has been transferred here through transformations from higher layers. Here, I can define the desired package. For example, I decide to use a particular package, assign a name to it, any name will suffice, and declare my intention to use this package before saving the changes. Subsequently, I will detail the package more thoroughly. To do this, I set the package name property to match the library provided by Microsoft and then save the changes. With that completed, I return to the process execution page and click the Done button to continue the process. The process advances to another manual task, where I am prompted to address the implementation concerns of the CQRS model. Similarly, this involves using specific packages for the CQRS model, such as those for working with a message broker or for event mapping, sending, and receiving. Defining this information is essential. Thus, I open the CQRS model at the PSM level and input the necessary package details. Some information has already been conveyed to the PSM level through model transformations from higher levels. At this stage, I only need to specify the details of the packages in use. For example, I define a package for command and set its package name property. I also establish a package for interacting with the message broker. To conserve time, I pause the video, define the packages, and then resume. Having defined the packages, I can now specify which packages are required by my commands, events, and command handlers. For instance, if the commands require a certain package, I go ahead and indicate that this package is needed. This step is repeated for all commands, including create, cancel, complete, and revoke order. Command handlers also necessitate specific packages, which I define accordingly. The same applies to events and their handlers. I define the necessary package for each. I believe all the packages have been defined. allowing me to mark this task as complete and proceed with the process execution. The process continues until we reach another manual task, which I will cover in a subsequent. Well, to complete this task, I need to describe the implementation concerns of the core domain. Similar to the previous two tasks, I must introduce the software packages that are required. For instance, if I need a particular package, I navigate to the core domain model at the PSM level and specify that this domain concept requires said package. Then I save the changes. I will proceed in the same manner for other elements. Next, I refine the package information and set the value of the package name property. With this, the model's information is complete, and I can click on the Done button associated with this task to resume the process. In this task, as well as in another where we describe the implementation concerns of the controller model and the task related to the CQRS model, what I essentially did was manually describe the necessary software packages. If you have a working convention and typically use special or predefined packages, these can be automatically added to the models using model transformation, assuming you know in advance which packages you intend to use for your project, as I do. Therefore, these three manual tasks, one showcased in this video and two in the previous one, can be automated using transformation patterns, eliminating the need to manually describe this information. Well, there is just one more manual task remaining to complete the MDD process. I will record this task in another video and provide an explanation. At this stage, I wish to address the concerns associated with implementing the interfaces related to the data repository. If you recall, in the previous steps, we defined collaborators linked to the command handler and event handler. Among these, we had two interfaces, iOrder repository and iCustomer repository, designed to interact with repositories and assist command handlers and event handlers in performing their tasks and meeting the requirements. Currently, I am at the PSM level. These interfaces have been automatically transitioned to the PSM level using model transformations. My aim here is to delineate the operations included within these interfaces. For instance, for iOrder repository, I intend to include CRUD operations to create, read, update, or delete data. I plan to describe this information within the CQRS model at the PSM level. Hence, I will open this model, and you will observe that these interfaces have been migrated to this model through transformations. For iOrder repository, I will declare that it encompasses these operations and then save the modifications. I also define the customer repository operations in the same way. Now I am able to refine these operations with greater precision. Take create order async as an example. I can designate its name, set its output value to task, assign its visibility as public, and define its input parameter as order. Additionally, I can outline the body of this operation before saving these changes. Subsequently, I will configure the properties of delete order async in a similar manner. Based on this information, I will refine the operations with more details. To prevent the video from becoming overly lengthy, I will pause the recording, complete the data entry, and return. I have now defined the operations. For instance, create order async is named accordingly, its output is task, its visibility is public, it accepts an input named order, and I have described the body of this operation for more detailed elaboration. Similarly, for delete order async, it is named correspondingly, its type is task, its visibility is public, it requires an input called order ID, and this constitutes the body of this operation. In a comparable fashion, we explicate the information pertaining to update order ASIBC. Regarding the get order async operation, its output is of order type and it accepts an input parameter named order ID. For the list order async operation, I have specified its output value and also the body of this operation. Since I am at the PSM level and the implementation platform is based on the .NET framework, utilizing the C# language, I have effectively entered a portion of the implementation code here. Furthermore, I can refine the parameters utilized in these operations, such as order, order ID, customer, and customer ID. For instance, I desire the name of this parameter to be order and its type to correspond to the order concept. For order ID, its name should be as stated, and its type should be guide. Similarly, for the customer parameter, I set its name to customer and its type to a concept named customer. For the customer ID parameter, its name is customer ID, and its type is guide. I mistakenly defined the parameter type as customer in the video. If desired, I can complete the body of the create order async operation within the repository using the C# language. This approach can be applied to other operations to finalize their operation bodies. Instead of attempting to complete or adjust the solution code later, I describe these details within the models themselves for future utilization. I will pause the video here to keep it concise, enter the information, and then return. I have also described the operations body information. For example, you can see that I have delineated the model to create an order, delete an order, update, and retrieve a list of orders. Similarly, I have described the operations related to customer in further detail. Now I can return to the MDD process, click the Done button for this task, and proceed with the process. We observe that the process has ultimately concluded. I have executed the process of transforming models from the CIM level to the PSM level. In a subsequent video, I will demonstrate how PSM models are transformed into code by initiating a process that generates C# code. Before running the code generation process from the models, it is necessary to specify and define the settings for your project. To do this, I navigate to the problem domain section, specifically the order subdomain. In model number 16 at the code level, I define the project along with its settings and dependencies. In the .NET ecosystem, you can find software packages on the NuGet website and add them to your project. NuGet serves as a package manager. For instance, let's consider two packages for my project. 1. MDDPlatform.SharedKernel. This package provides a set of base classes that I'll use in my project. 2. MDDPlatform.MessageDispatcher. I intend to use this package for message dispatching. The first step involves naming your project. The name you assign will be used in the generated code output. Once I click the Create Instance button and provide a name, I proceed to define its dependencies. In this case, I specify that the project relies on the two packages mentioned earlier, MDDPlatform Shared Kernel and MDDPlatform Message Dispatcher. Note that the package names are optional, and you can choose any name you prefer. After saving the changes, my project is created, and the two packages appear in the designated section. To provide more detailed information, I click the Edit button. Here, I specify the package ID and version for each package. In the same way, I enter the package ID and version for this package and save the changes. With my project and its dependencies defined, I'm ready to run the process of generating C# code from the models. I'll document this step in a separate video. The model-driven development process has been successfully completed, with all its steps finalized. The models have been transformed from the CIM level to the PSM level. Now my goal is to generate solution code from these PSM models. To achieve this, we've defined an additional process that implements these models in C# based on the .NET platform. I navigate to the Process Management section and select the second process responsible for generating code from the models. Similar to the previous process, if this one isn't already configured, I need to set it up. Upon entering this process, I find that the configuration hasn't been defined yet. Therefore, I proceed to create a configuration for it. This process consists of two phases. First, the mapping phase brings the models from the PSM level to the code level. Next, in the subsequent phase, it converts the code-level models into files that can be downloaded and stored on the system. Initially, I set up a configuration for it. First, I select the problem domain, which specifies the input and output models needed for the configuration of the tasks. Next, I delve into the configuration section to set up the tasks that constitute this process. Detailed instructions for configuring these tasks are provided in an attached file, along with accompanying videos. For instance, the first task involves selecting Model 4 as the input model and Model 17 as the output model. Similarly, for the second task, I designate Model 4 as the input and Model 17 as the output. I pause the video, configure the settings, and then return. After configuring the task, I'm ready to create an executable process. Clicking the Create Executable Process button accomplishes this. Now I can proceed to run the process. In the configuration section, I click the Execute Process button to access the execution page. Notably, this process doesn't involve manual tasks. All tasks execute automatically upon clicking the button. To obtain the code, I head to the Problem Domain section and select the Download Project Code option. Here I specify the problem domain and choose the output model containing the solution code. In this case, model number 19 project solution. Rather than storing the code as plain text, I've modeled it using a simple metamodel. Consequently, the system looks for the file concept. I define a concept called project file as my file. It prompts me for file name information, which I provide via a property called file name. Additionally, I specify the content of the file using a property named content. For the file extension, I use an attribute called extension. Lastly, I indicate that the file storage path can be derived from the value of the relative path property. This information, stored in the model, guides the code generator in creating a compressed file containing the project code. After downloading the code, I extract it into a folder to explore its contents. I find commands such as create order, revoke order, and cancel order. Handlers have been created for each of these commands, with collaborators added to their respective class constructors. The code also includes controllers, e.g., order controller, defined entities, event classes, e.g., order created, order canceled, and corresponding event handlers. Notably, an event handler for customer-created handler is also generated. Additionally, interfaces, e.g., customer repository, order repository, and their methods are present in the folder. This code represents the solution for my project, written in C# on the .NET platform. One of the factors that can enhance reusability is the ability to locate artifacts previously created in different projects and reuse them when needed. In MDDPlatform, you can search for and retrieve models you've already created across various projects. To access this feature, navigate to the Problem Domain section and select Query Domain Model. Here your search can be based on the problem domain, subdomains, model names, assigned tags, abstraction level, or the language used to describe the model. You don't need to fill in all these options. Choose the ones that align with your requirements. For instance, if I want to search by language and find all models created based on the CQRS metamodel, the system returns models from different subdomains. To narrow down the search, I can specify the problem domain, such as searching within the product subdomain. Alternatively, I can search by tag. For example, if a model has the controller tag, I can retrieve it. This search operates at the model level, utilizing the parameters visible on the page. Additionally, you can search among the domain-specific languages, DSLs, you've defined. To do so, go to the DL Managements menu and select the Query Languages section. Here you can search for languages based on their building block concepts. Suppose I want to find a language containing the command handler concept. Running this search yields two metamodels. The first is domain-driven design, which upon opening reveals the defined concepts and their details. Similarly, for the CQRS metamodel, you can explore its constituent concepts. You can search for multiple concepts simultaneously. For instance, I entered command handler and event. As a result of this search, I identified 4 languages that incorporate the command handler concept, the event concept, or both. Although the search functionality is still in its early stages, due to MDDPlatform being a research product, these capabilities hold promise for improving reuse. Suppose you want to reuse portions of the information from models you've previously described in another project and transfer them to new models. For instance, let's say I want to transfer data from a CRAC model to a model based on the CQRS metamodel. Why would I do this? Well, in the CRAC model, I have concepts like command, domain concept, and event. While in the CQRS model, I encounter concepts like command, command handler, event, and event handler. Upon closer examination, I notice that the command and event concepts are common between the CRAC and CQRS models. It seems reasonable to transfer some of the commands and events defined in the CRAC model to the CQRS model. How do we achieve this? Let's start by navigating to the CRAC model. From the top menu, we'll enter the Reuse Model section and declare our intention to reuse this model. On the subsequent page, I specify the destination model, the one into which the data should be integrated. For example, let's transfer information from the CRAC model within the orders subdomain to the CQRS model in the products subdomain. This is just an illustrative example. After selecting the subdomain, I indicate that I want to integrate this information into the CQRS model. Clicking the Reuse button triggers the system to read the CRAC model information and merge it with the CQRS model information. This integration adheres to the rules and constraints defined in the CQRS metamodel. For instance, while the CRAC model includes the domain concept, this concept isn't defined in the CQRS metamodel. Consequently, information related to domain concept won't be transferred. However, since both metamodels share the command and event concepts, data related to these will indeed be transferred. Now, if I navigate to the product subdomain and open model 04, which corresponds to CQRS, I can observe that information from the CRAC model has been successfully transferred. Commands now reside here, and events are located there. Additionally, if there are relationships between concepts in the source model that align with those in the destination model, information about these relationships will also be transferred. Keep in mind that if the relationships differ between the source and destination models, as in this example, that information won't be transferred. This tool feature enables seamless integration of information from one model into another, whether they share the same meta model or have different meta models.